Good evening, everyone. We are in the week 12 problem solving session of the NPTEL course, Control and Tuning Methods in Switch Mode Power Converters. And week 12 is about performance comparison and simulation. I am Teja Golla, a fifth year research scholar working under Dr. Santanu Kapat at Embedded Power Management Lab, IIT Kharagpur. Let me share my screen. Let me know once you can see my screen.
Yes, sir. The screen is visible.
Okay. So in this week, sir has shown some comparative case studies of small signal versus large signal model, and he also discussed about the digital aspects, how we can digitize, what are the challenges and advantages of the digitization, and what changes does it make in the overall control system. And then he has actually spent one entire 1 hour lecture summarizing what we have discussed in this entire course. So I have gone through the assignment and I have checked what problems they have asked. They are not exactly related to what Sir has taught in the week 12. So I thought I'll just summarize what Sir has told in that main lecture towards then, and then I'll solve few problems, and also I'll be explaining regarding the digitization aspect. There is another course of Sir, which is digital control in switch mode power converters and FPGA based prototyping. That is the continuation of this course where Sir has explained the digitization and how to implement using FPGA the digital control of a switch mode power converter. So in this lecture, I would like to start with what we have discussed in this entire course, just to summarize so that we'll be clear what has been covered. And if you have any doubts, you can ask regarding that. Else we'll just proceed with the summary, and then I'll solve few problems, and then we'll move on to the digitization aspect. Is that clear?
Yes, sir. Yes.
Okay. So I'm just taking what all he has mentioned in that lecture 16. So I'll just be referring to that lecture to summarize what has been discussed in this entire course. So, summary of this course. So Sir has mentioned in multiple ways. First, he has summarized what was discussed in the course, and then he has discussed about what modeling techniques that we have covered and what type of controller designs we have discussed, and different type of control architecture that we have explored. All these things he has explained in detail. I will also just quickly go through the summary. So first, we have discussed about the modulation and control techniques. So first we'll go details in the summary, and then we'll go one by one further details. And then Sir has also discussed about modeling techniques, different types of modeling, starting from state space modeling to small signal modeling, large signal modeling, how accurate they are for voltage mode control, for current mode control, and also for the modulation techniques and control techniques. We have discussed different types of modulation, pulse width modulation, and then we have discussed. Sir also has highlighted about phase shift modulation, and then fixed frequency modulation, variable frequency modulation, constant on time, constant off time, hysteresis, as well as control techniques. We have discussed about voltage mode control, current mode control, hysteresis control for both fixed frequency as well as variable frequency, and hysteresis, of course, is variable frequency. And then once we do modeling, it's always important to do the model validation using the simulation. So in this, we have discussed model validation using simulation. So whatever modeling, small signal modeling, large signal modeling we have done, how do we know that that is correct? So we should always validate any model anywhere, not just limited to this course. Everywhere we have to model and check whether the model is valid or not, and how accurate it is. So there can be limitations. There may not be limitations. We have to check what approximations that we are making in process of getting the model, and how accurate it is in capturing the dynamics of the converter using the simulation. Then once the model, large signal model is validated, then we have moved to the small signal model. So we have discussed small signal based design. And then we have seen that once we get the small signal, we have seen that first we got the open loop transfer functions, and then we have validated it, and then we have moved on to the closed loop for voltage mode control. What type of transfer functions we'll be getting, which is same as GVD. But in the case of current mode control, we have made some approximations and we got the first order approximated model. And then we have also seen how accurate that model is in order to use it for the controller design. And we have seen that it is more or less accurate because it is first order. It is, like kind of overdamped, second order overdamped, the response will be similar to that. And then we have validated it with the switch simulation and we have checked in one tenth or one eighth of the switching frequency. It is closely matching. So we can use that model to design the controller, and we have designed the controller, and we have also checked the responsibility whether it is matching or not. So all these aspects are is covered in this like previous weeks. Then we have also discussed about the performance limits because of the small signal. Because we have seen that the small signal model is valid in 1/10 of the switching frequency. And it is not valid beyond that because of the approximations or averagings that we have done in the model development, and that will limit the performance. And in terms of bandwidth, if we speak, it will limit the bandwidth till 1/10 of the switching frequency. So now we cannot use that. So what else we can do to improve the performance beyond this limit? So then we have discussed about the last signal model and also the switching model, where we have not considered any approximations and we have learned about the trajectory, vector field, etc. So we have discussed about the last signal model. And then we have also discussed about the switching model. So we have seen that during the on state, what is the trajectory? During the off state, what is the trajectory? And then we have also discussed about the vector field. So why it is important? So we have also discussed about the eigenvalues as well as eigenvectors. And then we have seen how the trajectory is going towards the equilibrium point. So we also have to learn what are equilibrium points, how the trajectory is moving, how to get the direction using the vector field, and what type of equilibrium points exist, stable, unstable, focus, all these things, saddle point, everything, node, stable node, stable focus, unstable focus, and then center and then saddle point. All these things we have learned. We have also solved quite a few problems. So we have learned about the vector field, and we have also learned about its geometric interpretation. Okay. So once we have done this, then we have used this model to design the nonlinear control methods, and how we can use that model to design the controller. So Sir has discussed about the sliding mode control and boundary control, various control methods. So we have learned about the nonlinear control methods, what type of nonlinear control methods that exist. Sir has explained all these nonlinear control methods, and then we dive deep into the sliding mode control. And also, Sir has explained the boundary control as well. Then we have also seen the last signal tuning methods, where Sir has explained the trajectory-based tuning for both voltage mode control and current mode control to achieve optimal performance. So Sir has explained for voltage mode control as well as current mode control and how to achieve the time optimal performance in one switching cycle. And then we have also derived the gain expression and how to get the gains using the model, etc. We have learned, and we have also derived. So we have seen how the performance can be improved, also energy efficiency, because the switching is happening with the number of switchings that it takes to reach the new operating point is less, so the switching losses will be less. So we have seen the performance and efficiency benefits. And then in this final week, sir has discussed about the digital control architectures, which I'll also be teaching towards the end of our discussion. So this is like the summary of what sir has taught in this entire course, just to give an overall picture or overall idea. So any doubts till this point before I further summarize what modulation and what different type of modeling techniques that we have used, what type of small signal models that we have learned. Any doubts until this point? Anyone? Okay, no doubts. Then
No,
I'll
sir.
just okay. So then I'll just summarize what all modulation techniques that we have discussed. Overview of modulation techniques. Okay, so sir has discussed about the fixed frequency modulation techniques as well as variable frequency modulation techniques. Also variable frequency modulation technique. So here we have seen PWM based modulation technique in fixed frequency. So we have discussed about the pulse width modulation. And then we have discussed here constant on, flash off, and then also hysteresis. So how we are going to get the uh, gate pulse and which modulation technique we are going to use. All these aspects we have discussed in the modulation techniques. And also, sir has mentioned in this current week that variable frequency is an emerging trend where people will be using in the products. So sir has also emphasized on the variable frequency, also the stability aspects, because variable frequency offers better stability than fixed frequency, whereas fixed frequency has so many limitations. Like in the case of current mode control, for certain peak current mode control, the duty ratio has to be less than 0.5. For valley current mode control, it has to be greater than 0.5, as there will be stability issues in the system. Whereas in the case of variable frequency, you don't have such limitations over the entire range of the duty ratio. It is or it will be stable. So we have also discussed about some stability aspects. Also, sir has discussed about the performance aspects in terms of if you have constant off time. So off time is constant, on time is variable. So step up performance will be better. Whereas in the case of constant on time is fixed and off time is variable. So step down performance will be better. So we have seen the performance aspects as well as the stability aspects where sir has mentioned in this weak where fixed frequency modulation techniques suffer from subharmonic instability, whereas variable frequency have a wide range of stable operating region. Also, we have discussed about some design aspects, how to design the controller for both the cases. And then we have also seen some protection aspects also in terms of you know current limit, because the peak current has to be limited to protect the circuit, and for variable frequency, so we have this minimum on time, minimum off time. We have thoroughly discussed why we need minimum on time, and we have also discussed why we need minimum off time. Also, the system will collapse or it will reach VDD. So either it will go up or it will be keep on charging or it will be keep on discharging. So in order to stop that, we need to have certain protection so that we'll have minimum on time or minimum off time. Also, we need to have current limits sometimes so that the current will not keep on increasing. So if the current limits, then we'll forcefully turn it off. So all these aspects under modulation techniques we have discussed. So any doubt until this point, anyone? Any questions? Okay. So just a few more things I wanted to summarize. So till now we have just discussed about what all sir has covered in this course and what type of modulation techniques that we have discussed, and all these things we have discussed for both voltage mode and current mode. We have discussed about sorry, voltage mode control as well as current mode control. Voltage based constant on time, constant octave, current based constant on time, constant octave. We have discussed, and hysteresis also voltage based as well as current based, and same we have done for the fixed frequency. Now we can also see the overview of modeling techniques that we have used. So we have also learned different types of modeling, right? So we have started with the small signal modeling. We learned about the small signal modeling. So first we got the small signal model, and then we have validated it and we have used it to design the controller. Then how did we get this small signal modeling? From the equivalent circuit model, right? So we got the equivalent circuit model, and from there we got this small signal model. And then we have obtained the small signal transfer function from this small signal model. Got the small signal transfer function from the small signal model, and we have used to design the controller. So all these were used to design the controller using small signal model. Controller design using small signal model assist. Okay, then we have seen that there is limitation. Again, I'm stressing on this point because it is very important. So we have seen that we have bandwidth limitation. We have bandwidth limitation. And then we have moved to the large signal model, where we have not considered any approximations and we have considered the model as it is. And then we have also discussed large signal based controller design. And then using this, we were able to get the time optimal performance. Okay, so we have seen different type of modeling techniques and different type of models, their advantages, benefits, as well as challenges, and then how to overcome that, and which model could be the best one to get time optimal performance, and how to get that model, how to validate it, as well as how to use the large signal based tuning to achieve time optimal performance, and what will be the trajectory in order to achieve time optimal performance, and using the trajectory, how can we shape the to achieve time optimal performance, how can we shape the trajectory, and how to get the gains to achieve that response. So all this we have discussed. Again, I'm just quickly summarizing. So till this point, any Doubts or any questions? Things clear or any queries? Yeah, we can ask.
Sir,
Yes,
in
yes.
week two,
Okay.
discontinuous conduction mode operation of buck converter was discussed.
Yes.
So two equations are given in the PPT for
Okay.
I0 and V0. So can you give the steps how to derive that expression
Okay.
for
Okay.
discontinuous conduction mode?
Yes, yes, yes. So again, thanks for pointing this different, mode of operation. So we have also discussed about different modes of operation. Different modes of operation of the converter, which is based on the inductor current. So we have CCM, continuous conduction mode, BCM, boundary critical conduction mode, sorry, not BCM. We have CRM and DCM, right? Critical conduction mode and the discontinuous conduction mode. First to right, this is critical conduction. So you wanted the condition for it to operate in the DCM, right?
Yes, sir. In DCM, an expression for I0 and V0 are given.
See, there are two things. One is for the discontinuous conduction mode, what will be the V node expression, and the other one is what should be the load resistance for it to operate in the discontinuous conduction mode. So which one are you asking exactly?
The condition for CCM boundary condition that is clear for me.
Okay.
That expression for average inductor current and average output voltage.
Okay.
For example, in CCM it is D into V in, but
Yes.
for
Yes.
DCM some other expression is given.
Yes.
So
Yes. Yes. So now, if you see, let me draw the plate first. So we have something like this. So in the case of CCM, there is no issue. But whereas in the case of DCM, what happens is the inductor current will rise and then the inductor current will fall and then it will become zero. So now you have to see, say I'm considering a buck converter. So let me draw a buck converter. Okay. So now we have considered this, say this is D1 TS and say this is D2 TS. Then this region will be 1 minus D1 plus D2 into TS. So the whatever we do, everything remains same. What exactly we are doing here is uh, in the case of continuous conduction mode, we have two voltages for the inductor, right? So in this region, what will be the voltage of the inductance? VL, voltage across inductance.
V in minus V0.
Okay. And in this,
Minus V0.
okay. And in this,
0.
0. So now if you see, the voltage is not exactly The same for the entire 1 minus d1 ts. So now it has a this what do you call, different voltages, three types of voltages. Now if you do average VL equals to 0, we'll be getting d1 into V in minus V0 plus previously what we used to get 1 minus d1 into V0, right? But now we are not getting like that. We will get 1 minus d1 minus d2 into minus V0, right? So this minus d2 is the additional term that it is coming because for this d2 ts VL is 0. So now if you calculate, we'll have d1 into V minus d1 into V0 plus, so minus if I take common, minus into d1 V0. Here also if I take minus common, we have 1 minus d1 into V0 plus d2 into V0 is equals to 0. Agree?
Yes, sir.
So now if you calculate, we will get d1 into V. This entire thing, what is like simplified term of this entire thing? Minus V0, right?
Minus V0.
Yes, minus V0 plus d2 into V0 equals to 0. So now can you tell me the expression for V0?
D1 by 1 minus D2 into V.
V1 by 1 minus d2 into V. So ideally, if we are in continuous conduction mode, d2 is 0. There is no d2 because there is no region during which VL is 0. So if d2 is 0, V0 is d1 into VL. But if there is discontinuous conduction mode, and if you want V0, then you will get d1 by 1 minus d2 into VL. So now the question is how to find d2 because d1 is what we are giving, d2 is what is coming from the circuit. So till this point, is this clear? How we got V0? Is it, this is clear, right? This is coming from average inductance voltage is 0.
Yes, sir. This is clear.
Okay.
But in the slides, another expression V in divided by 1 plus UL into I0, something else was given.
So I think the sir might have calculated the D2 expression and made some approximation. So like you have to that is just the final expression, but you have to understand how we are getting that. So now we have gotten this expression V0 is D1 by 1 minus D2 into V. So now another thing that we know is average inductor current IL is equal to output current, right? So average inductor current IL is equals to I0 because IC is 0. So we'll get V0 by R. Average inductor current is V0 by R. Now again you have to see what is the average of the inductor current, right? How much is the average of the inductor current that you will be getting. So now we will get this base into height, half into this base into height. So if this ripple is delta IL, so the average will be half into, so we'll get V0 by R equal to half into base. What is base? Half into d1 minus, so 1 minus d2 into ts into delta I. So now whatever you are telling, let us just check. So now you can substitute 1 minus d2 in this expression and then you can get things, right? In terms of is this clear? If you substitute 1 minus d2, here you will get V0. So you take this V naught on the other side, and then everything you will get in terms of V naught. Basically, here we do not know what is D2, so we have to find D2. So that D2 I am finding from the average current. So the average current is uh, half, sorry, by TS will be there. So this TS will not be there. So this is half base into height into delta L by TS. So this is what we will be getting. So one we are getting from the average current. So the average current is this. This is my I naught. And then we have obtained this expression. Is that clear? Whoever has asked.
Yes, sir.
Okay, so now let me just quickly summarize the DC and AC equivalent models that we got. So overview of DC and AC equivalent models. So using the circuit averaging or state space averaging or average switch model, we got the equivalent model, right? Equivalent circuit model. And we have used different techniques for the same. We have used circuit averaging, average switch model, or we also have state space averaging. State space averaging. So we have used three different learned about three different techniques to get the circuit equivalent circuit model. From there, we got the DC equivalent model. We also got the AC equivalent model. So from this AC equivalent model, we got the small signal transfer functions, I should say. And then using the small signal transfer functions, we have calculated the yeah, sorry, we have used to design the controller. So we have put the controller with that. So these are the different type of models that we have obtained using the equivalent circuit model and how we have used that to, design the controller. So this is just a simple aspect. If you have any queries, else we'll go to the controller design aspect. So overview of controller design, overview of I will say voltage mode control, overview of voltage mode control. So what we have done is we have learned about the first control architecture, how we are getting the gate pulses in voltage mode control, and then once we have understood the architecture, we have obtained the small signal models. Small signal models and validation, which is very, very important. And once we have learned this, then we have learned about the small signal controller design. How to design using the small signal, what type of controller we are going to use. So we have learned about PID, then we have learned about practical PID and ideal PID. Then we have also seen type 3, we have more uh, freedom to like achieve or tune bandwidth as well as phase margin, whereas in the case of PID, we have only fixed phase margin and bandwidth is adjustable. So in the case of PID, we have learned that ideal and why do we need practical PID. So all these aspects we have discussed in the voltage mode control, and then we have moved to current mode control, and then we have done almost the same thing. So let me just copy paste. Okay. So overview of current mode control. So in the case of current mode control, everything is same except we have PI here and then type put. So PI, there is no issue like derivative. So we have PI controller tuning and then we have type to compensator. And then one more thing I would like to add here, we have done small signal controller design and then we have also done large signal controller design to achieve optimal performance. Then here also we have large signal controller to achieve time optimal performance. So till this point, any doubts you have? And then in the case of large signal controller design, again, just to like again summarize, we have first taken the large signal model and then also the switching model. And then we have learned about the vector field and the trajectory, how the trajectory moves, how to calculate the vector field and how the trajectory moves towards the equilibrium point. Again, whether it is stable equilibrium point, unstable equilibrium point. And once it is going to the equilibrium point, how the switching will help us to go from one operating point to another operating point in one switching state. And in such cases, what will be the trajectory and what will be the mathematical expression. And then how to design the controller for that, how to get the PID gain so that it will reach the new operating point in one switching cycle. And then sir has shown the simulation and sir has also shown the comparison between the large signal as well as the small signal tuning and how it can improve the performance. And one thing about large signal or time optimal performance or like large signal tuning. It's the optimal performance. So performance is optimal. And here we have reduced V naught undershoot. So if the undershoot is reduced, then we have reduced capacitance, right? And then we have reduced settling time. And then if the capacitance is reduced, we have high power density. Optimal performance and energy efficiency because reduced switching during planning. So there is less than a minute. Once this meeting ends, kindly join. The summary is over, then we'll solve few problems. So reduced switching events, reduced switching during planning. So any doubts until this point? Once the meeting ends, we'll join back and solve few problems. Anyone? Any doubts? Please join back so that we can discuss few problems and then we'll move to the digital aspects of the controller. Can you see my screen?
Yes, sir.
So now let us solve few problems. One problem I have taken similar to that of assignment. So anyone how to solve this such problems? Okay, just give it a read or maybe I will read it out. Consider a plant transfer function given below. GP of S is 1 by S plus 1 into S plus 5. So a closed loop control scheme is applied to the plant according to the figure below, where GC of S is an ideal PID controller as shown, which is GC of S is KP plus KI by S plus KDS. So here we are considering ideal PID controller, but In the case of practical implementation, you can consider KDS by tau ds plus 1, where tau d is very, very small or very, very smaller value than 1. And then from there, you can keep one small value of tau d just for the practical aspect. So determine the value of Kp, Ka, Kd such that the desired closed loop characteristic equation becomes s cube plus 20s square plus 10s plus 0.1 equals to 0. Then in such case, find Kp, Ka, and Kd. So anyone, how to solve this problem, or how to do this?
First, we can write down the characteristic equation 1 plus GC of S into GP of S equal to 0. Then we can equate the similar terms.
Okay, okay. So that's a nice idea. So let us start with that. So we know if you want to know the closed loop transfer function, we can get say G closed loop output to input. We'll get GC into GP 1 plus GC into GP. So now the whatever is there below, this is corresponding to the characteristic equation. Characteristic equation. So now you need to get this expression 1 plus GC into GP. And from that characteristic equation, you need to find Kp, Ka, Kd. So just note down GC is Kp plus K by S plus Kd into S, which is an ideal PID controller, whereas GP of S is 1 by S plus 1 into S plus 5. So can you solve and then get the gains of Kp, get the gain values Kp, Ka, Kd. Then once you get the values, then I'll cross check. So in the meantime, you just give it a try and then solve. So the hint has been given. Now we have to solve and get. So I hope you are solving. I'll just give 5 more minutes and let's see who got what values. And then once I start doing, then you can cross check if you are getting the answers or not. So this is Kp is 5, K is 0.1, and Kd is 14. So let me wait for others, then I'll check whether I'm also getting the same answers. So all of you, please give it a try. The hint has already been given. Uh, Another person says, Arun says Kp is 5, K is 0.1, and Kd is 14. So both of you are getting the similar answer. So Parvati, I hope you are also trying. Once you also give, then I'll start solving.
Yes, sir. In between, I made a mistake. So trying again.
Okay, okay. You just give it a try. Take your time. Then once you get the answer, let me know. Then I'll start solving.
Yes, sir. I also got the same answer.
And we are also getting the same answer. So let me just solve it and then people who have difficulty when they refer to the video, they can understand. So Sonali, the question is, I have given a plan transfer function, which is GP of S is 1 by S plus 1 into S plus 5. A closed loop control scheme is applied so that the plant is being controlled by a PID controller as shown here. And they have given the characteristic equation, which is S cube plus 20 S square plus 10 S plus 0.1 equal to 0. And then we are asked to find KBK KD. So first we need to get the characteristic equation, which is the denominator of the closed loop transfer function. And the characteristic equation is 1 plus GC into GP. So let us calculate 1 plus
Yes,
GC.
okay, sir.
Okay. So GC is KP plus KI by S plus KDS. And then GP I have given 1 by S plus 1 into S plus 5. So this is the characteristic equation. So this we are actually RHS is this expression. So let us let's simplify it and then show. So we have KD into S square plus KP into S plus KI by S into 1 by S plus 1 into S plus 1. So we have S cube plus 6 S square plus, if I'm making any mistake, kindly let me know, IS plus K2 S square plus KPS plus KI. So this is my overall characteristic equation. So we have S cube plus KD plus 6 into S square plus KP plus 5 into S plus KI, which is now equal to this expression S cube plus 20 S square S cube plus 20 S square plus 10 S plus 0.1. So from here, we can directly get KP, KI, KD. So KP is 5, as you have said, and KD is 14, as you have said, and KI is 0.1, as you have said. So I hope all of you have done it correctly and then getting the answer. So now before I hope this problem is clear to everyone. Sonali, are you able to understand and get the same answer?
Yes, sir, I'm trying to solve.
Okay.
So nearby that, yeah.
Okay. Once you do, you let me know, then we'll move on.
Yes, yes.
Are you able to solve? Hello, Sonali.
Yes, sir, I'm trying, but I'm not getting this step. 1 upon S plus 1 and S plus S
S
at
plus
that
5,
moment.
S plus 5, S plus 5. This is
Huh.
5, sorry.
Okay, so when we are taking this second step, I'm not getting. So I'm trying to by the equation.
Okay. So until this point, is this clear?
So maybe by mathematical some mistake is there from my side.
Okay. So should we wait or should we move on? What do you think? So,
Is it fine? I'm trying to solve
yeah,
this
yeah, it's fine,
second
it's fine,
step.
it's fine.
Yeah.
In the meantime, I'll just give another, uh, you know, uh, I'll give another problem for others. So what I'm trying to do is, so entire thing remains same for the same problem. Let us see if I, instead of 1, if we make it 10. So if we increase the plant DC gain by 10, we want to see how the controller gains are changing. So just others, please try this. In the meantime, I'll wait for Sonali. So I'm just showing the screen. And then we'll see how the DC gain affects the controller gains, PID gains. I hope others are solving the other problem. Let's wait for Sonali and then let's move on together. So Riddhi is saying KP is 0.5, KA is 0.01 and KD is 1.4. Okay, let us check whether the answer is correct or not. And then we'll see. So according to you, the gains have become by 10. So let us see if that is correct or not.
Same, sir. All the values got divided by 10.
Okay.
Yes, sir, I'm able to solve the third step.
Okay.
Yeah.
So you got these gains?
Yes, yes, sir.
Okay. So now let us move to the other problem where I have given gain to be DC gain to be 10 instead of 1. So if we see this has become 10 now, and this also has become 10. So now let us solve. So basically from this I can say that previously there was 1. Now I have multiplied by 10. So if I divide these by 10, then the equation remains same. Which also again let us solve and then check. Okay, so we have s cube plus 6s square plus 5s plus 10 kd into s square plus 10 kb into s plus 10 ki equal to 0. We have s not equal to 0. That's the expression. Well, s cube plus instead of s square we have 10 into kd plus 6 s square plus 10 into kp plus 5s plus 10 into k. Now this is equal to the characteristic equation. So instead of like normal KP, KI, KD, we have 10 into KP, KI, KD, 10 into KP, 10 into KI, 10 into KD, because we have multiplied by 10. So now, if you calculate whatever you are getting, so KP will be 5 by 10, 0.5. And KI will be 0.1 by 10, 0.01. And KD will be 14 by 10, so 1.4. So all the gains are divided by 10. So if there is any DC gain, the gains have to be reduced or divided by the same DC gain. Say similarly, if I have a sensor here, now say if I have a sensor here with the gain of say half. So then what will be the gains if sensor gain is half? Say sensor gain is half. So can you tell me what will be the gains now without solving, just from the intuition that or whatever we have understood in now? Divided by 5. This is 0.5. So should we divide by 5 or what should we divide it by? So these are the gains that we got with DC gain 10. Now I have DC gain 10 plus additionally sensor gain 0.5. So the DC gain is already 10. So DC gain of the plant is already 10. Now in addition to that, actually I should not say DC gain because the DC gain is not 10. DC gain is 10 by 5 too. So let us not call it DC gain. So the numerator, I would say, because DC gain is not 10. So the GP numerator is 10. And on top of that, sensor gain is 0.5. So what will happen to the gains multiplied by 0.5 divided by 0.5 divided by 5? So Riddhi is saying 1, 0.02 and 2.8. So how are we going to get those? Into 0.5 or divided by 0.5? Riddhi? So whatever is the gain in the loop, we have to divide the gains by that gain. So previously there is only 10, right? So now we have divided the gains by 10. Now if I'm adding additional 0.5, I need to divide the gains by 0.5, right? So the gains have to be divided by 0.5. Yes, so divide by 0.5. So we have KP now it becomes 1. So multiply by 2 basically, 0.02, and then KD will become 2.8. So that's how we are going to get the gains. And then that's how we'll have to see. Ideally, in the simulation, when we are designing the gains, we'll design the gains. But in the hardware, there can be sensing gain because sensing gain is not needed in simulation. So there can be sensing gain or there can be some other gains like sensor gain. Say sensor has reduced and because in order to implement it, you have further reduced. So say there are some gains in the system. So then how you will get the gain? So from this idea, you can say that if the gain is X, then you have to divide by X. So if the gain is Y, if you will divide it by Y. So you need not recalculate everything again in order to get the same performance. If there is a gain in the system, you have to divide the gains by the same amount so that the overall characteristic equation of the performance remains same. So is this clear, everyone? Yes, sir. Okay.
Yes, sir.
So now,
Yes, sir.
once
Yes,
this
sir.
part is clear, okay. So once this part is clear, I have given something similar. Just check this part. So I have given a first order transfer function, say current control, and then I have given a PI controller, and then I have given a characteristic equation. So the order of the system will reduce. So now how are we going to get the gain? So this will also be simple because we have solved that problem. So once we solve this, then we'll move to the final discussion of today, which is the digitization aspect. And all other problems in the assignment are given from the previous weeks, like ripple based or fixed frequency on time calculation, and then pole zero cancellation. So this type of problems we have not solved in any assignment, so that's why I have taken this problem. But all other problems are similar to what we have discussed earlier. So I thought, let me not redo it again because they are already recorded and uploaded to YouTube. Let me just discuss something that we have not discussed, like digitization or this type of problem. Sarun is saying KP is 10 and K is 0.6. So let us wait for others and see what others are getting. So someone is saying, Riddhi is saying KP is 10 and K is 0.6. Arun and Riddhi are getting the same answers. Let us wait for Parvati and Sonali and then we'll start solving. K is 0.2. Arun is saying K is not 0.6, 0.2. So Riddhi, you also cross check. In the meantime, I'm waiting for others to solve. And then once you solve, I will also start solving.
Sir, KP is 10 and KI is 0.2, I thought.
Okay, so you're getting KP is 10 and KI 0.2. I think Arun is also getting the same. Riddhi is also saying yes, 0.2. I think who else is solving? Let's wait for the last person and then we'll start solving. So Sonali is saying K is 0.2. And how much KP you're getting, Sonali? Six. Okay. So I guess now everyone has solved. Let us start solving. So the same characteristic equation. So I'll directly skip that part and then I'll write directly 1 plus GP into GC, right? So we are finding the expression of 1 plus GC into GP, which is 1 plus GC is KP plus KMX into GC is 3 by S plus 4. Now if we expand this, we will get S square plus 4S plus 3 KPS plus 3 KI. So we know S square plus 3 KB plus 4 into S plus 3 KI, which is equal to S square plus 34S. Is 0.6. If I reduce 4, it becomes 30 divided by 3 becomes 10. So KB is 10 and K is 0.6 by 3. So K is 0.2. So 10 and 0.2 is the right answer. Yes. So now, if we add a sensing gain of say 110, say sensing gain. H or capital H is say 0.1 or 110. So I have a sensing gain of 0.1. So then what will be the gains? Anyone, if you want to calculate, or from the previous logic also you can predict what will be the gains. So KP, Sonal is saying KP is 100. Riddhi is saying KP is 100 and K is 169. Okay. K is 2. Sonal is saying K is 2 and Riddhi is saying K is 169. Let us see. What about Arun? Let's wait for Arun. Once he also gets the answer, then we'll solve.
102.
102. Okay, let us check. So because we have divide by 10, sorry, we have a product of 0.1, we have to divide by 0.1 or multiply by 0.1. So now the new gains KP and KP dash will be KP into 10, which is 100, and KI dash will be KI into 10, which is 2. So we have 102. So that's how we get the gains KP dash as well as KI dash. So is this clear for everyone?
Yes, sir.
Okay. So now we'll move to the digitization aspect. Digitization now. Say this is voltage mode counter, but also digitization of analog counter. So from where is the difference coming? So previously there is no digital PWM in the circuit. Also there is no analog digital conversion. So if we like this is what we call digital control. So if we write the analog control, we don't have these terms, right? So then how was it looking? It was looking something like this. We have digital components over. Then we have driver. And then we have switch mode power converter. And then we know. And then we have sensing. This is our traditional analog control. And so we have V reference. This is V naught, everything in time domain. This is digital compensator or analog compensator because this is analog. So we have analog compensator, and then we have driver here, and then we have switch mode power converter SMPC, and then we have sensing. So this is our analog control. Okay. So now, if you see, here it is V naught and here it is V naught, sensing like V naught sensed. But here if you see, say this is V naught, here we have V naught of N. So this is digital. And then this entire thing. So this entire thing is digital. Now this is in digital way. So it needs an analog to digital conversion or analog to digital converter, which is also called as ADC. So once we have the ADC, the V naught is sampled and then it is converted into V naught of N. So the V naught is converted to V naught of N, and then now the V naught of N is subtracted from the V reference to generate the error voltage, which is again a digital error. So this becomes V error of N. So this is V error of N. And then now this is passed through digital controller, because previously we have analog controller. Now this is passed through digital controller to get the digital control voltage. Previously we are getting analog control voltage. Now we are getting digital control voltage. So once you get the digital control voltage, this digital control voltage has to be used to generate a PWM signal. So instead of using PWM, we are using digital PWM. So now we'll also get into the details of how the digital controller, PID controller will look like. Also how the, a digital PWM will function and what are the benefits as well as what are the challenges, etc. We'll discuss. But till this point, do you have any question before we go into the details of sampling and etc. etc. Anyone, any questions? No questions, or if you have any questions, you ask, I'll explain in detail, because we have more things that are coming up. If things are clear here, then we can move further, else we'll spend time here before we move further. No queries?
No query, sir.
Okay. So now, first is the analog to digital converter, ADC. Why do we need this? So we will digitize the V naught. So basically what we are doing is sample and hold. We are taking the sample and then we are holding that value, right? Sample and hold. So the question that will come is, at what rate can we sample, or at what rate should we sample? So you know that Nyquist frequency happens at half of the sampling frequency. So we have F Nyquist is equal to sampling frequency by 2. So this should not interfere with the the switching frequency. So if you take one sample per cycle, then it will become FSW by 2. So that can be filtered out. But if you take more samples, say 5 sample per cycle, which is 5 FSW, then Nyquist frequency will become 2.5 FSW, and then it will have an interference. So that will cause certain instability, which are like limit cycle oscillations. So that sir has explained in his lecture. We'll not go into the details because that is beyond the syllabus of this course. So we have to sample once in a cycle. If we don't sample once in a cycle, but if we sample once in 2 cycles or once in 3 cycles, then it will have like subharmonic oscillations, because we are taking sample like once in 2-3 cycles. So I'll explain what will happen if we sample more or if we sample less. If we sample more, we'll have limit cycle oscillations. If we sample less, we'll have subharmonic oscillations. Okay. So at what rate should we sample? So the answer of this question is 1 sample per cycle. Okay. So if we are sampling once per 2 cycles, then what happens? So basically in digital, wherever you are taking sample, that point will be regulated, right? In analog, the average voltage is regulated at 1 volt. But in the case of digital, the point at which you are taking sample, that will be regulated. So for example, so I'm considering 2 cases. Okay. Um, so this is my regulated voltage. Okay. So now say my voltage is like this. Something like that. Need not be the exact shape. So in this case, what I'm doing, I'm taking sample at the value point. So the value point is regulated at the reference, which is this is V reference. So here also this is V reference, and this is V naught, of course. Now if I'm taking at the top point, then the waveform will look like this. Okay, because I'm taking at the peak. So now the peak point is regulated. So it matters wherever you're sampling. So if you want the average value to be regulated at V reference, then you have to take at the midpoint, like the on-time midpoint or off-time midpoint. So there are multiple ways of doing. In the case of average current mode control, you are taking average, something like that. Here also you can take sample in between the on-time or off-time. Again, there can be a question: how do we know on-time? How do we know off-time? So you can take at the middle of the switching frequency. But in the case of constant on time or constant off time, one of the value is known, so you can take at the middle point. But in this case, the objective that I'm or the point that I'm trying to make is, if you are taking the sample at the value point will be regulated. If you are trying to take the sample at the peak, then the peak point will be regulated. So now I'm taking once in a cycle, so that one point or that one point in each cycle is ensured that it is at the V reference. So now let us do, say, 5 samples, once in 5 samples or once in 5 cycles. I'm taking sample once in 5 cycles. Okay. And say this is my V reference. So now in this case, what happens? So we are taking once in 5 cycles. So basically what I'm doing is I'm taking this point 1, 2, 3, 4, 5, and I'm taking this point. So these 2 points are supposed to be on the V reference. What about the other points? They can be some kind of oscillations. So we do not know. So let us see. One possibility is say we are taking this condition just to make it easy for sampling or basically drawing. So I'm taking say value point so that I have more space above the line. I can draw it better. That's why. But logic is applicable even if you do it in the other way. First of all, there is less than a minute. If this meeting ends, kindly join back. So we will have like this: 1, 2, 3, 4, 5. 1, 2. Again, 1, 2, 3, 4, 5, and so on. So now if you pay attention very clearly, you can see so this is my V reference, and then this is my V naught. Because I am taking my sample once in 5 cycles, say 1, 2, 3, 4, 5. And again 1, 2, 3, 4, 5. Again 1, 2, 3, 4, 5. So my digital controller will ensure wherever I am taking sample, that point will be regulated at V reference. So other points can be anywhere. There is a possibility that it can be above V reference or below V reference. I have considered one of the possibility. So now if you see, actually, this is the time period, right? This is the time period THW. So this is the switching time period, or we'll get the switching frequency. But if you see, this is actually another periodicity, right? Which is 5 into THW. Agree, everyone? Because it is happening once in 5 cycles. This is 5SW, which is now corresponding to a frequency of FSW by 5. So which is a fraction of switching frequency. So that's why it is called subharmonic. Harmonics are product, integer product of FSW, like 3 FSW, 5 FSW, they are harmonics. But fraction of switching frequency is called subharmonic. So that's why it is called subharmonic oscillation, because it's an oscillation. So that's why if you sample like less sample per cycle, or I would say once in more number of cycles, then that will lead to subharmonic oscillations, which are like, I feel I could made you understand what are subharmonic oscillations from this figure. So is this clear, or should I explain once more to make it more clear? If you have any doubts, please ask. I'll explain again. But if you don't have any doubts, then also you will mention so that I'll be able to help you understand.
Clear, sir.
Clear. Okay. Others?
Okay, sir, no issue.
Okay, clear. Okay, so that's why wherever we are taking sample, that is very important, because that point is only uh, on the at the regulated point. So the controller is ensuring that point is regulated. So if you want it to be regulated every cycle, then you have to take it every cycle. But if you take more than once, then in between, the controller will try to change the value. So that will affect. So if you are trying to change multiple times within the cycle, then that will cause something called limit cycle oscillations. So that is advanced topic, which is not needed in this course. So that's why I have not touched. But subharmonic oscillation is something you can correlate and then imagine and then get an idea. So that's why I have drawn a figure where you can see that these points are lying on V reference. Others can be above and also can come below. It need not be just above or just below. It can go above and below. So the frequencies FSW by 5 or FSW by n. So that's what is called subharmonic oscillations. So now, because all these are happening because of the sampling. So the sampling is first of all uh, causing an issue. How many number of samples, or how many, what is the frequency at which we need to sample? So that itself is causing an issue. Also, there is a delay, right? So ADC will have also a delay, because the moment we ask it to take sample to the moment it gives us the sample, there is conversion and some delay will be there. I hope you know that ADC will take time, a few number of cycles. So the frequency at which the ADC is sampling, that is also like the, or I can say the clock frequency of the ADC is also important, because if the clock frequency is high, then it is computing at a faster rate, then the delay is less. But we are taking one sample per cycle. I can have ADC running at very high frequency, but I'll take only one sample once in a cycle, so that my delay is small. So the delay, which is basically coming from the conversion, conversion delay. So because my ADC is trying to convert, it will have some delay, of course, and then that delay is again will cause issue in the systems that have shown some hardware results. So it will cause issue. So now the ADC itself is causing two kind of issues if we don't pay attention to it. So one issue is the conversion delay, and the delay in the system will cause issue. And then the other thing is at what rate we need to sample, so that will also cause issue. So now we have discussed about this part, where is it's about A to D conversion, and then we have seen that it can cause some issues and we have to be very careful about it. Now let us move to the digital PWM. I hope whatever we have discussed about ADC conversion, I think it is clear. We have not gone into the architecture of ADC like SAR ADC or pipeline ADC, flash ADC. That's a different thing. That's not covered in this course. It will be covered in the other course, digital control switchboard power converters and FPGA based prototyping. But we are basically discussing the fundamentals of the ADC, like at what frequency you need to sample, then its conversion delay. So if this part is clear, then we'll move to the digital PW. Any queries until this point? Okay. So I hope no queries. So in the case of analog, we have analog sawtooth, and then it is compared with the control voltage. Whereas in the case of digital, digital is a number, right? So you have digital counter, which will count with respect to one clock. So it has finite resolution. Whereas analog, it's a sawtooth RAM. So it is like charging a capacitor and it has infinite resolution because it is analog. Whereas this has finite resolution. Okay. So, and these vertical things are because of the quantization. So there are two things that I would like to highlight here. So first you understand counter, right? In the digital counter, it will start from 0, 1, 2, 3, and then say it resets at 99. Let us assume that it is starting from 0 and then it is resetting at 99. So let us consider each step or some single step in between. So the vertical height is because of the quantization. This is a quantized voltage, right? So this can be some, V minimum, like minimum control voltage that will be used in the computation. Say this is say 1 millivolt. Then say this is this value is say 10 millivolt, and then this is 11 millivolt, and then this is 12 millivolt. So now because of this quantization, I don't have the intermediate values. Like my control voltage cannot be 10.5 millivolt. My control voltage cannot be 10.6 millivolt. Either it can be 10 millivolt, or it can be 11 millivolt, or it can be 12 millivolt. But in between, the resolution is gone because of the quantization. Now, this is the clock, T clock, at which we are updating the counter. So the counter is updating at some main clock. So using this main clock, now we are updating the counter. So if I need, say switching frequency of, say like I am using T clock to be say 10 nanoseconds, and I want T switching frequency to be 1000 nanoseconds or 1 microsecond. Then I need to have 100 such counting, right? So I need to count 100. So if I multiply 100 with 10 nanosecond, I'll get 1000 nanoseconds. So basically I'm counting from 0 to 99. So in that way, I will count. Say if I want 2 microsecond, I'll count to 199. If I want 5 microsecond, I'll count to 499. So again, it depends upon the main clock and the switching frequency that you need. So both of these things will decide how much is the counter or how much to how much value you should count using the digital counter. So this T clock will decide the time resolution of the duty ratio. Okay. So are these difficult or are you able to understand? If you face difficulty, please let me know. Then only I'll know that what is happening here. Else I'll keep on going and you will not understand. Are these things clear? Arun, Parvati, Riddhi, and Sonali.
Yes.
Yes, sir.
Yes. Okay. So now you see the quantization. Uh, why is my video showing? So the quantization will not let the control voltage to have, it can be any value. It will not let the control voltage to be any value because it has a quantization in the vertical scale. Now, if we see in the horizontal scale, the same thing happens. So because the incremental time is in terms of T clock, say I have something like this. So, like, assume that things are okay because I have just drawn. Ideally, it should be equal spacing vertically and horizontally, but let us assume that this is my control voltage, something like this. So now, if you see, if you have the comparator, I have duty ratio something like this. But say control voltage has slightly increased and become like this. And became like this. So now this is my new control voltage. So if you see the duty ratio also in the horizontal scale, it's a multiple of T clock. So the minimum duty ratio delta D will be T clock by TSW, right? Because I again cannot have infinite resolution for duty ratio, because either I can have T clock by TSW is the minimum duty ratio I can get. After 0, the minimum duty ratio that I can get is T clock by TSW. Next is 2 T clock by TSW, 3 into T clock by TSW, up to so on counter value into T clock by TSW, which is 1. So the duty ratio is incrementing in terms of T clock by TSW. Is this point clear to everyone? What is the minimum resolution for the duty ratio? Is this point clear?
Yes, sir.
Okay. So now for the above example that I have considered T clock 100 nanosecond and TSW 1 microsecond. What is my delta D?
One by 100.
1 by 100. Very good. So it is 0.01. So my duty ratio cannot be 0.355. It can be 0.35 or it can be 0.36. 0.355 is not possible. Okay. So now I have finite resolution vertically in terms of control voltage and horizontally in terms of duty ratio, which are infinite in the case of analog control. So in the case of digital control, because of the quantization, both vertically and horizontally, I have limitations in the smallest incremental value of the control voltage as well as the smallest incremental value in the duty ratio. Are these two things clear? How we are correlating the vertical axis as well as the horizontal axis?
Yes.
Yes. So now, what will be the problematic case? So let us consider one challenge that we are going to face. So it would be easy if I start with the duty ratio. Say my delta D is 0.01. Minimum duty ratio is 0.01. But my calculation says that duty ratio at steady state will be 0.305. So in this case, what will happen? What do you think will happen? Like my implementation will not let me have the resolution of 0.001. It has 0.01 means either I can have 0.3 or I can have 0.31, right? So my implementation will make sure that either I will have 30 or 31, right? So how can I get 305? So any idea, any thought process? So this is 0.30. So if you see from the control perspective, say buck converter, if I have the duty ratio less than the required duty ratio, my output voltage is lesser than the required voltage. So the error is positive, so the control voltage will increase. So if my duty ratio is again above the required one, then my error output voltage is above the reference, error is negative, so it will try to decrease. Until and unless I reach the point, either I am below or I am above, but not at that point. So what is going to happen? What do you think is going to happen?
It will oscillate in that band.
Yes, very good. So very good. So it will try to oscillate between 0.3 and 0.31 so that the average will is 0.305, because the output voltage average in the average sense, it will become V reference. So just how it is happening here, like how it is oscillating. the same way here also the duty ratio will oscillate because it will not find that one solution. It will either be slightly above or slightly below. So whenever it is going above, my controller will ensure that it is coming below. Whenever it is coming below, my controller will again make sure it is going above. Above, below, but it is not finding that one particular solution where it can reach. So now what happens? It will oscillate between 0.30 and 0.31 such that average is 0.305. So that's why resolution is very important. If I don't have finite resolution, like very small resolution or very high resolution, I should say, very high resolution or very small delta D, then it will have less oscillations. But say if I want to have 0.005 and say my delta D is say 0.1 and the duty ratio that I am trying to achieve is 0.105, then it will oscillate between 0.1 and 0.2. So you can consider there will be 5 cycles of 0.1 and 95 cycles of 0.2. So there will be, so many oscillations. But if I have delta D to be 0.1, delta D to be 0.01, then it will oscillate between 0.11 and 0.12. So which is very close. So if the duty ratio resolution is not good, then it will oscillate between big values. If it is small, then it will oscillate between small values, which might be reasonable for our application. But if it is oscillating big duty ratio, the output voltage also will swing between 0.1 into Vin and 0.2 into Vin, which is again not a good way of designing the controller because the output voltage is swinging, which has to be actually tightly regulated. So that will cause issues. So is this clear? What will be the challenge in the case of digital? Again, it's an interesting problem how to solve this. We are not going into the solution at this point. We are trying to just think about the problem that we are going to face. Is this clear?
Yes, sir.
Okay, so now this thing we have discussed in the time domain, like in the x-axis. Now let us see what will be the issue in the y-axis. So this is one type of challenge. So can you guess what could be the issue in the y-axis? Like in x-axis, we have seen that duty ratio, if it is not perfectly aligned with the resolution, there is an issue. So now can you think of something that can happen in the y-axis? Anyone, any idea? Okay. Someone has mentioned in the chat. Control voltage oscillate. Very good, Riddhi. Say my control voltage. My control voltage is this. There is no headache. I will get the. There is no headache. I will get the duty ratio accordingly because it is aligning with that vertical resolution. For example, now let us take that my control voltage is this. Then there is a problem, right? Because vertically say this is 1 millivolt, right? Say this is say 1 millivolt, and then in this case say Vcon is 2 millivolt. 0, 1, 2 millivolt. So say assuming this is 0 millivolt, 1, 2, 3, 4, 5 millivolt. So say it is oscillating between 0 and 5 millivolt. Now here Vcon is what? 3.5 millivolt. But my controller implementation is in such a way that it will have only 1 millivolt resolution. So my control voltage can either be 3 millivolt or it can be 4 millivolt. So what happens now? How to get, because my output is output will be regulated if my Vcon is 3.5. So if my Vcon is 3 volt, it is less than the required voltage. If it is 4, then it is more than the required voltage. So how is it going to settle, or what is going to happen? How can I achieve Vcon to be 3.5 millivolt? Anyone? We are encountering the same kind of problem vertically, which is again reflected in the horizontal. So either time in the time scale or in the V naught scale. So y or x axis, we are just correlating. So same problem happens here when the resolution is not, so finite or like infinite resolution. We have finite resolution here. Here also we don't have infinite resolution. Whereas in the case of analog, let us do this. Say in the case of analog, the sawtooth will be something like this, right? So it has finite resolution. So it can take any value. But now we don't have that flexibility. We are limited. So can anyone tell me what will happen if the Vcon is 3.5 and then we have 3 millivolt or 4 millivolt? Something similar to what we have discussed just now. Oscillate, yes, very good. Oscillate. So it will again oscillate. Maybe 3 millivolt, 4 millivolt, or sometimes it can come or go above, but it will oscillate and try to maintain the average at 3.5 millivolt. So now you can say that over a period of 5 cycles, the average is 3.5, or over a period of 10 cycles, the average is becoming 3.5. So now you see the time period is or a switching frequency is 1/10 of the oscillation frequency is 1/10 of the switching frequency, or 1/5. So again, these are called subharmonic oscillation. So now if you see, just by digitizing, just we have introduced digital. I have not even still discussed about the controller design or anything about the noise or any practical implementation issue we have not yet discussed. Just the basic thing that we have discussed is one, because of the sampling, where to sample and how many times to sample, and delay. That itself was causing issue in the ADC and digital PWM because of the finite resolution. I may not be able to get the exact duty ratio value, or I may not be also able to get the exact control voltage value. So this itself is a headache at the very basic. So now with the implementation, there will be many challenges and then many issues we are not going to discuss here, but in the other course, sir has discussed about this. So the digitization itself is causing issues. So then you can ask me, sir, then what will be the, like, what are the benefits? Because in the case of digitization, say digital control, first of all, it's everything is digital, so it is immune to noise. Because in the case of analog, the noise can change the value, right? So it is immune to noise. Also, the values the PID gains can be changed because it is digital. I can change the values, right? PID gains can be changed. In the case of analog, you will design using op-amp, right? PI, R, C values. You have to choose R and C values. So now I can choose like finite PID gains, and the PID gains can be changed. And also there is no aging of the resistors, no age effect, no aging of R, C, and op-amp. So we can use an FPGA or a microcontroller. Everything is inside, so there is no aging. Say R value will change, C value will change. That will affect the PID gains. So the PID gains also is fixed. PID gains are not unaffected by the tolerance of resistance or capacitance. Say even if the resistance and capacitance changes, here there are no resistance and capacitance. It's a digital number in the FPGA or microcontroller, so there is no headache as such. So now another thing is I can change the PID gains in the like real time. So I can change the gains in real time because it's like a like a digital control which can take action. I can write a code. If this happens, do this. If that happens, do that. Whereas in the analog, you will be needing a lot of circuit, right? So in the case of analog, you need a lot of circuits, which means cost will increase. Also, the area will increase. Whereas in the case of digital control, we say same IC. I am just writing the code and dumping in the same IC. So the size is fixed. Or I can make a custom controller IC also. And I can implement complex algorithms by writing the code. Implement complex algorithms. It may be very difficult to implement. Maybe difficult to implement using op-amps. Right. So op-amp, using op-amp, say I need some kind of complex algorithm. I will write the code, Verilog or whatever code, and then implement in the controller. I'll not bother about how it is implementing that. I'll be bothered about whether it is working or not. Whereas in the case of op-amp, you have to connect op-amps and resistors and capacitors and see whether it is happening. Say resistor is slightly changed, then it will have effect. That all the headache is not there in the case of digital. So it has benefits and also it has challenges. So like it's how everything works, life and everything. Nothing is perfect. There can be some pros and there can be some cons. So nothing is all good or nothing is all bad. So analog control has its pros and cons, infinite resolution, etc. Simple implementation is simple, but there are certain other issues like PID gains can be changed. Like in the sense the values may not be perfect. It can be changed over time. There can be aging effect, and then the op-amps required can be more, etc., etc. can happen. So is this clear? This part?
Yes.
Okay. So now this is one digital voltage mode control. I will not be going in detail because that is not the part of the course, but I'll just uh, explain what are there and trying to make you correlate. So in the case of analog, we have output voltage and then directly error voltage is generated. But here we are digitizing it. So output voltage first is converted into a digital number, subtracted from a digital V reference number to get digital error. Whereas in the case of analog, till here we have analog error. Now it is digital controller generating digital control voltage compared with the digital sawtooth, which we have just seen here. This is the digital sawtooth, whereas analog is straight line, digital is staircase compared with the digital control voltage to generate the set reset pulses. And then this is like a free running counter to generate the counter, and then it is being compared. So don't bother about this. Basically, we are getting everything in digital. So everything is digitized. So just very rudimentary basic explanation of differentiating between analog and digital. So is this clear? Where the changes are different, like where the changes are coming for analog and digital?
Yes.
Okay. So now without going in further detail of PID controller, I'll just briefly explain. In the case of continuous time, ideal, again, I am considering ideal. So in the case of continuous time, things are in S domain. If I'm doing in discrete domain or digital, it will be in Z domain. So first thing, it is ideal. So continuous domain, I'll have GC of S is KB plus K by S plus KBS. So now if I break this down, so we have GC of Z domain, digital domain. KP remains KP. 1 by S will be 1 minus Z inverse, and KD S will be KD into 1 minus Z inverse. Let's not go into the details of how it is coming. I'm just telling, just for knowledge purpose, that this is how the difference will happen. There it is in digital domain, S domain, Z domain, and here it is in analog domain, which is S. So this is analog S, analog. So that's the S domain. This is digital. So that's why it is in Z domain. Is this clear? Then I'll just quickly summarize and then we can wind this session. The discussion is basically summary. Again, I'm just summarizing the summary, so I'll just do it quickly. So in week 1, sir has discussed about the summary of everything and then comparing things. And then also sir has discussed about the digitization aspects. So I have just quickly summarized the course where we have discussed about different modeling and modulation techniques, control techniques, and then validating it, and then small signal based design, large signal based design, vector field, and how to achieve large signal tuning based time optimal performance. And then we have also discussed about different non-linear control methods like sliding mode control, boundary control, and then we have coming to the week 12, we have discussed about some digital control architectures. And then in the modulation techniques, we have discussed fixed frequency, variable frequency, and then we have seen what are the differences in terms of stability, performance, as well as design, and also protection aspects. And then we have discussed about pulse width modulation. In variable frequency, we have discussed constant on time, off time, as well as the hysteresis control for both voltage mode control as well as current mode control. In the case of modeling, we have started with the small signal modeling that we have obtained from the equivalent circuit model, and we obtained small signal transfer functions using which we have designed the controller using small signal model. Whereas if we want to achieve a better performance, we have gone to large signal model and large signal based controller design, and we have seen the aspects of time optimal performance. And then we have also discussed about different modes of operation like continuous conduction mode, critical conduction mode, and discontinuous conduction mode, and we have seen how to get the boundary condition, as well as here we have seen how to get the V0 expressions. Then we have discussed about the AC and DC models that we have got from the equivalent circuit model using circuit averaging or average switch model or state space averaging. And using that, we have updated the small signal transfer function, which we have used for the controller design, again, small signal based. Then in the case of voltage mode control, we have discussed about the architecture, the small signal models and validation, and the controller design using PID, ideal or practical, and type 3, and how we can achieve better performance using large signal controller design. In the case of current mode control, same control architecture, small signal models and validation, and as well as small signal controller design, but here it will be first order system. So PI or type 2 is sufficient. And we have also discussed about the large signal controller design to achieve the time optimal performance, and how this performance can reduce the capacitance size because of the reduced undershoot and increase the high power density, as well as the reduced settling time and the reduced switching events during transient will save the energy efficiency or improve the energy efficiency. Then we have solved a couple of problems, very simple, based on the characteristic equation. So we have calculated the characteristic equation and then compared to get the KP KD values. And then we have seen if we multiply by some gain, then the gains have to be divided by that gain. So if we multiply by 10, then the gains are divided by 10. Then if we multiply by 0.5, we have to divide it by 0.5 or multiply by 2. Similarly, we have considered another a first order system and designed the PI controller, and the same thing we have done. And then if there is any sensing gain of 0.1, we have to divide it by 0.1. So the gains will be multiplied by 10. And then we have seen the digitization aspects of the analog control, and we have seen how the ADC is causing issues in terms of the conversion delay first and foremost, and then how many times or at what rate should we sample. That will also have an impact in terms of limit cycle oscillations if the sampling rate is higher than switching frequency, or it will lead to subharmonic oscillation if the sampling rate is lesser than the switching frequency. And then we have seen because of the finite resolution, there can be issue because of the quantization, vertically voltage level as well as the time level. So we have seen that there will be finite resolution. So if the required duty ratio is not a scalar multiple of the minimum delta D, then it can oscillate between two values. Similarly, vertically, if the control voltage is not a integer multiple of the resolution, then it can also oscillate, leading to subharmonic oscillations. And despite all these issues, there are many advantages of the digital control, and that's why everyone is moving to digital control nowadays. So every gadget that you see, phone or any device that you have, everything is digital control. Like everything that has to be regulated, like AC regulated, or in your car where the speed has to be controlled, everything is being digitized. So like your hair dryer where the temperature has to be regulated, everything is digitized because it has various advantages. Now at least people are trying to go from analog to digital. So then we have discussed about one digital voltage mode control architecture, and then we have seen few aspects of the PID control. So this is all about this week 12. And again, I'll take one summary session or problem solving session before exam on Wednesday, 6 to 7, day after tomorrow, where you can ask me questions, or I'll just go through my notes from week 1 to week 12, whichever you like. So if you have any more questions, you can ask, else I'll end this session here. Any questions? Sonali, were you trying to say something, or no questions?
No question, sir. But during the assignment, when we are solving the problem, so
Yes.
sometimes means in the numerical, sometimes I'm not able to solve. But now I will try to use that detailed solution, and if
Okay.
get the query, I will ask you in the next section.
Yeah, definitely. So we have talked to the
Yeah.
NPTEL team, and then we have asked them to share the assignment solution. So please go through the assignment solution and find your mistakes so that you can rectify in final exam.
Yeah. Yes. Thank you, sir.
Okay, thank you. So thank you for joining and making this interactive. I hope you got you'll get benefited from this session. So again, see you in our last communication or last meeting, which will be this Wednesday from 6 to 7. I wish you all the best for your assignment goal as well as your final exam. Prepare well and solve as many problems as possible so that you will not make any calculation mistake in the final exam. So with that, I'll end this session here, and I wish you all the best. Good night. See you again on Wednesday. Thank you. Thank you, Riddhi.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.
Thank you. Thank you, madam.